person in this conference.
Good evening, one and all. Is my voice clear to everyone? And the video also? Please tell. So, are you getting any lag between the video and audio? Any gap between video and audio to anyone? Is it fine? Right? So, in the previous class, we discussed some of the fundamentals of the ring theory. What is meant by integral domain, field, the basic definitions, etc. etc. So in today's session, I want to discuss about some other definitions as well as what is the problem solving methodology to show that a given set is a ring or not. So let us discuss the technique for solving the problems and some other definitions and results based on them. That is the objective of today's session. Is it clear? Right? So let us take the problem that let us take the set Q of root 2 defined by set of all A plus B root 2 such that A comma B belongs to Q. So our question is, we have to show that Q of root 2 comma plus comma dot is a field. This we have to prove. So we have given a set Q of root 2 where each number is of the form A plus B root 2 where A comma B are rational numbers, and we have to prove that this set is a field. That was the question. Clear? So to show that, we have to verify Q of root 2 comma plus is a abelian group. Distributive laws hold in it. And if you take the other one, it is also abelian. This thing we need to prove to show that the set is a field with respect to the regular addition and multiplication of the numbers defined on the set. Okay. Now the question is, if you look at the pattern, it means that every number which is of the form some value plus some value into root 2 will belong to the set where the values are nothing but rational numbers. This is the objective in writing the pattern of numbers in this set. Fine. So if you take the first thing that Q of root 2 comma plus is abelian group, so we have to verify the closure, associative, identity, inverse and commutative properties with regard to the operation plus on this set. So let us verify for that. So if you take two elements, say x equal to a plus b root 2, y equal to c plus d root 2 in the set, to verify closure law, we have to show that x plus y belongs to the same set. To verify closure law, we have to show that the sum of these two values again will belong to the same set. It is very simple. If you consider the sum, it is nothing but a plus c plus b plus d root 2. Since this is a rational number, because here a, b, c, d are rational numbers, so a plus c is a rational number and b plus d is a rational number, so this value belongs to q of root 2, as a plus c is a rational number and b plus d is a rational number. So did you get the concept of closure law here? How we are proving? Say, any questions you have? Right. Associative law is very similar. So if you consider three values there, I have taken x, y, you take the other one z also. Then you need to consider the part that x plus y plus z is equal to x plus y plus z. This we need to show. So for this, if you apply the words, x plus y is nothing but so this is equal to so if you consider the RHS also, that also will come the same value, therefore these two are equal. That is about associative law. Fine. Please take a note of that. Or you can adjust the terms here so that you will get that idea. Because here if you consider it is, you can write like so you can modify the values. Closure is always associative, that we agree. But while proving the infinite number of terms, it is a formal writing to show that these two values are giving same. Actually, closure is always give the associative property. So you can confirm by means of functions, matrices, polynomials, etc., etc. But here you have taken different set. So here we need to verify that this also holds correctly in this. Because generally with that we write that addition of rational numbers associative, addition of real numbers associative, addition of complex numbers associative. It is true, but here you have taken a different set pattern so that you need to verify this thing also. So whenever you have a different type of operation, always we verify for the associative. In group theory also you have done similar kind of thing, that I think we have done a problem. There you have defined that a circle B is equal to AB by 3. This type of problem we have done in group theory earlier in the beginning. There you have verified associative property also there by calculating LHS and RHS separately. Because there you have taken a different operation, so that we need to check whether associative law holds or not. It is our confirmation always that whenever closure law holds, associative law will come automatically. 99% is always true. You cannot get a set where associative law gets failed when closure is satisfied. That's why. Now, coming about identity, So coming for the identity part, so whenever you take the element a plus b root 2 in the set, so on adding what value, you will get x again. This value we call it as identity. And this element must be of the same form like q of root 2. Can you guess? What could be the element I should take here, which also will be in the same form and you should get x? It is simply, you can say 0 bar, the identity element is this. Because if you add these values, x plus 0 bar is nothing but which gives the same value again. So whatever the way you add, you can add the element either the left side or the right side, you will get the same thing x again. So this is the identity element in q of root 2. Okay. And coming for the inverse, so if you take x minus x is equal to, so if you add x plus minus x, so minus x is the inverse for x with respect to the addition, and commutative is very easy. So if you calculate x plus y, it is nothing but as per the previous values considered. So this thing you can write it as so x plus y equal to y plus x. So commutative property is also verified. Hence, with respect to the operation plus, it is an abelian group. You please take a note of this. After noting, please tell. Any questions for the approach on this problem? Say, shall I erase this? Right. Now I want to show that with respect to second operation, that is multiplication, we have to show that this set satisfies the 5 properties. So if you take x is equal to a plus b root 2, y is equal to c plus d root 2, so you consider x dot y. So I am verifying closure law with respect to the multiplication here. So on multiplying, you will get the value as do you accept for this x dot y is equal to simply multiplying the numbers? Please check. I have simply multiplied x and y. The value is AC plus 2BD and AD plus BC into root 2. The simple multiplication of numbers, usually what we do. Now, coming for associative property, I leave this thing for you. I say that you have to calculate LHS separately and RHS separately and make sure that these two are equal in the result. That we have to verify. Fine. So please check that. So that you have to do verifying the associative property there. And coming for identity, here whenever you take the element x, you have to multiply with an element so that you should get x again. So this element I am denoting with the symbol 1. So which is nothing but 1 plus 0 root 2. So if you multiply any x with this value 1 plus 0 root 2, you will get x again. You can cross verify that. Since the values, the coefficient in this expression 1 and 0 are nothing but rational numbers, this value by default belong to q of root 2. So 1 bar is equal to 1 plus 0 root 2 is the identity element with respect to multiplication in q of root 2. Okay? And we can check for commutative property also. As we have done the calculation of x dot y. So you can do y dot x also, or you can rearrange the terms, that also you can say. So x dot y is equal to y dot x, so it satisfies commutative property also. Now there is one thing left, that we have to verify the distributive properties, and we have to verify that if you take any non-zero element, multiplicative inverse it will possess. So we have to make sure that there is an element in q of root 2 which is nothing but the multiplicative inverse there. That we have to mention. So coming for distributive properties, we have to verify two distributive properties, left distributive law and right distributive law. Left distributive law, you have x dot y plus z is equal to x dot y plus x dot z. Right distributive law, x plus y dot z is equal to x dot z plus y dot z. Actually, we have to verify that these two properties will hold in the ring. Since the problem becomes very lengthy in writing the solution, so among these two properties, we will prove only one. Either we prove the left one or we prove the right one, and simply we mention that the second distributive law will be proved similarly. So we stick on finding the value for one law between the two. So if you take the first one, as you have taken x is equal to a plus b root 2, y is equal to c plus d root 2, and z is equal to p plus q root 2. Now let us apply the values there. It is nothing but, considering the LHS, you have x dot y plus z means c plus p plus d plus q root 2. On multiplication, you will get the value as I will simply write like this for convenience. So you can write the solution in single step. So it is simply multiplying the values. So while proving the distributive law, we follow the technique that while considering the left distributive law, where the value is x dot y plus z is equal to x dot y plus x dot z. So to show that this equation holds, I will calculate the LHS separately and RHS separately, and I will show that these two values are equal. They will give the same result. So I have calculated LHS. This is the value of LHS. Now I calculate the RHS. So I calculate x dot y, I calculate x dot z, and show that on summing up, you will get the same thing. So if you give a number, say this is equation 1, so you calculate the RHS value, give that equation 2. So from 1 and 2, this equality holds. That is the general procedure usually we do. Okay? Fine, all of you? Please check what we have done. Are you clear how we have calculated the LHS value there? I think it's the value, right? Any questions for anybody? So if you are doing, just do it now and confirm the answer. You have the same one or a distinct one after calculating it. Are you clear? Say, right? So among the two distributive properties, we prove only one property, that is the left distributive law. We write that similarly in the same manner we can prove right distributive law. There is no need to prove, because if you consider LHS and RHS, the simplification will take nearly half page. There is no need to write the second distributive law again. So we can take the advantage. You can skip that thing. Now, one last thing we have to show that Inverse property holds for every non-zero number in Q of root 2. Now let me say, if we have taken the value a plus b root 2 in Q of root 2. Now the question is, on multiplying with what value you will get 1 plus 0 root 2, because it is nothing but the multiplicative identity in Q of root 2. So what value you have to take here to show that the multiplication of these two will give 1 plus 0 root 2. That is most important. So, and you have to ensure that the value what you have calculated here, this must belong to Q of root 2. Then only we say that every non-zero element has inverse in Q of root 2 itself. So for this, let us calculate this one. So if you rationalize the value, it will be so if you separate this part, please check out this. I have considered the value 1 by a plus b root 2, which is equal to that thing. So, as we have taken a non-zero value here, so the value what you have taken is not equal to the zero element. So obviously, either a or b is a non-zero number. If both are non-zero, it is well and good. Otherwise, at least one of a and b is a non-zero one. So definitely, this thing is also non-zero. Therefore, here we consider this value a by a square minus 2b square plus minus b by a square minus 2b square of root 2. We take this value here, and this is the inverse of a plus b root 2. Since a and b are rational numbers, this part is also nothing but a rational number. By default, it comes. Hence, you can cross verify that multiplying a plus b root 2 with this value will give 1 plus 0 root 2. You can easily verify that. Actually, there is no need to show that separately. We can write that this is the inverse of a plus b root 2 in Q of root 2. That's it. So we have proved all the properties so far considered. Hence, Q of root 2 plus comma dot is a field. That was the solution of the problem. So unless you have known all the 12 properties, you cannot prove that it is a field. All the properties must be known to you. How many properties you wish to show for the given set if you want to say it is a field. Fine. Please take a note of this. Then I take the other problem. Any queries for anybody over this? So are you comfortable with the solution? Say. Any doubts for anybody? Fine. Now on the whole, you can observe one thing, that the solution of the problem is very easy, but the procedure is lengthy, isn't it? We have to solve all the 12 properties on paper. That is the only drawback here. It takes much space while writing the solution. So here we define a new set. We call it as Gaussian integers. We denote with the symbol z of I, and some others will denote with the symbol j of I. So it is defined as set of all a plus ib such that a comma b are integers and I square equal to -1. This set we call it as Gaussian integers. You can simply understand that it is a subset of complex number system. We define complex number system in this way, accepted. We take all the elements of the form a plus ib, where the coefficients are real numbers and I square equal to -1. So if you fix, or if you put a constraint that the coefficients are only integers and I square equal to -1 as it is, such type of set we call it as Gaussian integers, and we denote with this symbol. And the interesting thing is, this set is an integral domain. But not a field. Now let us discuss this. So this is the problem I take now. Clear? So what is meant by Gaussian integers? Clear to all? Now the approach is very similar to the previous problem. So whatever the properties you have considered earlier, the same properties we are going to prove again and again here. So in order to show that it is an integral domain, you have to show that it is a commutative ring with unity and without zero divisors. It is a commutative ring with unity and without zero divisors. So if you have shown this, it means it is an integral domain. You have proved that. You have proved that it is an integral domain. Now, how to show that it is not a field, we will discuss later. And as per the definition is considered, you have to show z of I comma plus abelian group. So distributive laws hold here. So with respect to z of I comma dot, you have to prove for 4 properties: closure, associative, identity, commutative. Inverse we will not show here. If we have proved inverse, it will become a field, as it is given in the problem that it is not a field. So inverse property will not hold here. So you have to verify closure, associative, identity, inverse, identity, commutative. And how we take the elements here? If here you take x is equal to a plus ib, y is equal to c plus id. So if you consider x plus y, it is nothing but a plus c plus I into b plus d. If you consider the closure with respect to the multiplication, so x dot y is nothing but regular multiplication of complex numbers. It is ac minus bd plus I into AD plus BC. So did you observe the similarity between the previous problem and current problem? The approach is very similar. There you have taken root 2, here you have taken just I. Remaining all the things are very similar. Verifying the properties, closure, associative, identity, inverse, etc. etc. So here in the previous problem, you have mentioned the identity element as 0 plus 0 root 2. Here we mention the identity element as 0 plus 0I. In the previous one, you have taken multiplicative identity, the unity as 1 plus 0 root 2. Here we take it as 1 plus 0I. So each and every step of the previous problem will be reproduced here. So are you able to do it? Tell me. All of you. Any queries for anybody? If you want to show a property, I will show how we are going to prove it. Is it required? All right. So I want to prove one interesting property that without zero divisors I am going to discuss. How do we show that Z of I will not contain zero divisors? That we prove. Now let us discuss that, and I prove that it is not at all a field. That also I want to discuss, because other properties you are able to solve on your own as per the previous problem discussion. If you consider, are you comfortable in solving that or not? If I give an assignment for you, proving that Z of I is a ring, say, are you able to do it? Right. So again I write the set Z of I is equal to set of all A plus IB such that A comma B are integers, I square equal to -1. Now if you look at that, what is meant by zero divisor and no zero divisor? So zero divisors means we take two elements which are non-zero, but the product is 0. No zero divisors means if the elements are non-zero, so product is also non-zero. So to prove this value in a comfortable manner, we will show that if product is 0, then either x0 or y0. As I already discussed in the previous class that if you want to show the statement P implies Q, it is better to prove negation of Q implies negation of P. So this is just like the statement P, this is just like the statement Q. So apart from showing P implies Q, we will show that negation of Q implies negation of P like this. So if we have proved this, it has no zero divisors. Accept it all? Say. Right. Now let us take the part. So let us take that this is X and this is Y. What is meant by this 0 bar? Nothing but the 0 element. So if you multiply this, so equating the real part as well as the other part. Is it clear? Sorry, I have mistaken this. It is Z of I. Sorry. Thank you. Fine now? Yeah. So here you can observe that for the value a by b, you have two representations. So making that equal, you have, so cross multiplying this, you have accepted. Say, please check that. I have taken two values in Z of I, a plus ib and c plus id in Z of I. I assumed that the product is 0. So if you consider the product, it is nothing but 0 plus 0i. So making equated with the 0 element, so making the real part as well as the imaginary part with the coefficients, you get the result. There you have a by b has two equal values. One is d by c, another one is minus c by d. Equating these two, you will get c square plus d square equal to 0. All of you agree? Now, fundamentally, we have to observe that whenever you take a number in Z of I, always the coefficients are integers. A is an integer and B is an integer. So what happens here? C, D also integer. Whenever you square an integer, is it positive or negative? Irrespective of it. So here you can say that c square value is greater than or equal to 0 and d square value is greater than or equal to 0. Now what happens if you sum up these two values? The only possibility is c and d must be 0. Otherwise you will not get that c square plus d square equal to 0. The only possibility for c and d is these two must be 0. Otherwise you cannot get that sum of the squares of them will not be equal to 0. Accepted? Yes or no? Whatever the integer you take, if you square it, you will get a positive value. It is 0, then only you will get the value as 0. Isn't it? So, as you have taken that c, d values are 0, so you have y is equal to c plus id, which is nothing but 0 plus 0i, so 0 bar. So I have taken that whenever the product is 0, obviously one value is going to become 0. You can prove x is also 0, right? Because if you equate the expression for c by d. So here c by d is equal to minus a by b. Here c by d is equal to b by a. If you equate these two, you will get the condition as a square plus b square equal to 0. Applying the same phenomena here, you will say a and b values are nothing but 0, which gives that x equal to 0. So you can prove either of the way. Whenever you consider the product is 0, you can show that either y is 0 or x is 0. It is always possible. Fine. Therefore, it will not contain the zero divisors. That is the solution of it. Therefore, Z of I is just an integral domain. Now, there is one more part left in the problem, that is it a field or not? If you want to verify that, is Z of I a field or not, that we have to verify. Right? Now let us go for it. Are you clear about this solution? How we are going to prove that it will not have the zero divisors? Say, are you clear that? Fine. Now, Z of I is not a field. Let us discuss on this. So actually, while checking for the inverse, we have to show that every non-zero element in Z of I possesses multiplicative inverse. If this property is satisfied by Z of I, it becomes field. So, if you want to show that it is not a field, so we have to show that this property will not hold good. That means that you can find at least one non-zero element such that the inverse will not belong to that set. Inverse will exist, but inverse does not belong to the set. Okay? Are you getting the logic? The very basic example which you take is, you take the element 3 plus 4i belongs to Z of I. So what could be inverse of it? As I have already mentioned the technique of rationalization, you simply say that 3 by, say, the value as 25. You please check on that. How did I get this thing? Because 3 square is 9, 4 square is 16. If you sum up them, it is 25. So 3 by 25 minus 4 by 25 into I have taken. So if you multiply these two, you will get 1 plus 0i, which is the unity element. So this is the inverse of 3 plus 4i. You kindly check on this. Whether you will get the value as 1 plus 0i or not, you please check on that. You check and confirm the value. You accept it or not? The value. Say, right? Now the question is this value belong to Z of I? Is this value belong to Z of I? Say, no. Why? Because the very definition of Z of I is nothing but It contains the elements of the form a plus ib, where a comma b are integers. They are simply numbers. You cannot take the fractions there or rationals there. So 3 by 25 is a fraction and 4 by 25 is a fraction which does not belong to z. So this value you can say it will belong to q of I, as the coefficients are rationals. So this is not an element in Z of I. Therefore, you fail to get the inverse of 3 plus 4i, hence it is not a field. So one counter example is enough. Not only this value, you can take any value. You can counter example on it. Therefore, Z of I is an integral domain and it is not a field. That was the conclusion for the solution. So if you are clear with the problem solving approach, I just want to give some definitions. May I? Now we discuss one good definition, that characteristic of a ring. So what is meant by the characteristic of a ring? So characteristic of a ring is it is the least positive integer such that p into x equal to 0 for every element in the ring. That means you can take any value in the ring. If you multiply with this number, you will get 0. That was the concept of characteristic of ring. It is very similar to the definition of order of an element in a group. The order is the least positive number such that a power n is equal to identity. This thing we mentioned in the group theory. In a similar perspective, it is the least positive integer p such that px equal to 0 for every x in the ring. So for the whole set, whatever the x value you take, if you multiply with p, you should get 0. That we call it as the characteristic of ring. And whenever you cannot find such number, we say that the characteristic of the ring is either 0 or infinite. If you fail to get such positive integer, then we say that the characteristic of the ring is either 0 or infinite. That was the thing. And one good thing is, if you consider the ring of integers z plus dot, its characteristic is 0. Because by multiplying with 0 only, you will get 0 for every integer. If you take any other number apart from 0, you will not get 0 for the ring z plus dot. So the characteristic of the ring z plus dot is nothing but 0. Okay? Please take a note of the definition. And another thing is, if you consider about Boolean ring, the characteristic of the Boolean ring is 2. It is number 2. In a Boolean ring, 2x equal to 0 for every x. So this definition, you take a note of it. Then we discuss some small results. After noting, please tell. Now, the question is, let me take that the simple example. Now you forget about this 0. Now you consider the remaining values. Now I say that by multiplying what positive integer, you will get that px equal to 0 for all x in this set. Is it 1 or 2 or 3 or 4 or 5 or 6, what it is here? So you should verify the condition that px equal to 0 for every x in the set Z5. So what could be the number there? So if you multiply with this number p, you should get 0 for every value there. Can you say that 1 is the characteristic? Is 1 into x equal to 0 in that set with respect to multiplication modulo 5? No. Right. Is it 2? 2 into anything gives 0? No. Similarly, 3 into anything, 4 into anything or 5 into anything, please check. So whatever the x value you take in the set, you should get 0 on multiplying with that number. I say that 5 is the number because 5 into 1 is 0, 5 into 2 is 0, 5 into 3 0, 5 into 4 0. We accept it? Under the operation multiplication modulo 5, please understand. I am taking the remainder after performing the operation by doing division with 5. As you know what is meant by multiplication modulo 5. Accepted? Now the question is 5 a prime number? So the interesting thing is, you know that it is a field and it is also an integral domain. So whenever you consider the field or integral domain, its characteristic is always either 0 or a prime number. The characteristic of an integral domain is either 0 or prime number. That is true for field also. This is one good example you can observe. And if we have taken a finite set, it is correct. Now what happens? Let us take the set that you take the set Z46 with respect to the operation into 46 and plus 46. Now the question is, by multiplying what number you will get px equal to 0 for all x. So whenever you take a huge set, it is difficult for you to verify the characteristic, isn't it? Because you are checking for every element. I need to find a number such that by multiplying with that number, every element of the ring you should get 0. So for finite sets, it is comfortable to verify, but if you take the large sets, it is difficult to find. So based on this, one small result is given that you don't verify for each and every element of the ring. You simply take the identity element. Say the unity element, multiplicative identity you take. So you identify by multiplying what number I should make the unity element as 0. then that number is nothing but the characteristic. In a shortcut way, we say that P is the characteristic of the ring if P dot 1 equal to 0, where 1 is unity element in the ring, the multiplicative identity. So apart from verifying every x, you simply verify for only one element. So if you are able to calculate such smallest positive integer p, it will become the characteristic of the ring. That is the idea or shortcut you can consider. Okay? Are you getting it? Here, Z is not a field, but Z is integral domain, right? Z is integral domain. So its characteristic is 0. That's why I mentioned that the characteristic will be either 0 or a prime number. If you take integral domain or field, whatever the case may be, it must be 0 or a prime number. That we are going to prove theoretically. Whenever you take an integral domain, its characteristic will be always either 0 or prime. That we prove. Here it is Z5, not Z. Please check. It is Z5. The operation is addition modulo 5 and multiplication modulo 5. It is a finite set having only 5 elements. If you take the infinite set Z, it is nothing but so on, -2, -1, 0, 1, 2, so on. This set I didn't consider. I consider only this set. So on this set, we take the regular operations plus dot. And its characteristic is 0 only because it is an integral domain. Okay? Is the confusion clear? Right. Shall I erase this? Then I take a problem on how to find characteristic of a ring. So you consider the ring Z3 cross Z4. And what is its characteristic? So what are the characteristic of Z3 cross Z4? Let us discuss. Now here Z3 is nothing but 0, 1, 2 and Z4 is nothing but 0, 1, 2, 3. So you are taking the cross product between these two. On this set, the operations are addition modulo 3, multiplication modulo 3. On this set, the operations are addition modulo 4 and multiplication modulo 4. Now the question is, if you come up with the elements, it is the Cartesian product 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2, 2, 3. This is nothing but the set of ordered pairs taken in Z3 cross Z4. Okay? Yes or no? We simply write the regular Cartesian product A cross B of two sets. Now the question comes that how do you multiply here when two elements are taken there? There is an interesting question. Let me say you have taken one element 0, 3 and you have taken another element 2, 3. How you go on to multiply these two here in this set? What could be the result? It is also an ordered pair, right? Yes or no? Now the question is, you multiply first number with first, second with second. So here is, if you take the non-zero value, say, you can take non-zero value, say, let us take like this. So 1 into 2, 2, 3 into 3, 9. So actually, you have taken two operations, modulo operations. So this modulo operation belongs to the first coordinate. This modulo operation belongs to the second coordinate. So this is nothing but 2 and 1. Why? Because here on the second element, I apply the operation multiplication modulo 4. On the first thing, I apply the operation multiplication modulo 3. In this way, we perform multiplication over this set and addition also. Okay? This is the way we consider addition and multiplication over this set on the elements. Now the question is how to find the characteristic. Just now we discussed that. So apart from verifying each and every ordered pair, you simply have to take the identity element there, and if you check for identity, it is enough. So you need to find the least positive integer p such that p into identity element will give the 0. Right? So what is the identity element there in the ordered pairs? What is the identity element there in the ordered pairs? One comma 1. Why? Because in the first set, this is the identity element. In the second set, this is the identity element. The combination 1 comma 1 is the unity element. That is a good one. Very nice. So you need to verify that by multiplying with what number I will get 0. So there is no need to verify for the remaining ordered pairs. If you find a positive number such that by multiplying with that number, it should give 0, 0 as the result. So our objective is nothing but p dot 1 comma 1 is equal to 0, 0. This thing you should find. And what is p here? That was the question. Now you start taking the numbers. Suppose if you take p is equal to 1, so 1 into 1 comma 1 gives 1 comma 1 not equal to 0. If you take 2 into 1 comma 1, so nothing but 2 comma 2 not equal to 0. If you take 3 into 1 comma 1, this is nothing but 3 comma 3 which is equal to 0 comma 3. Why? Because on the first operation, first element we take multiplication modulo 3, and the second element we take multiplication modulo 4. So if you multiply with 4, it will be 4 comma 4, nothing but 1 comma 0. Because on the first element we apply multiplication modulo 3, and the second element we apply multiplication modulo 4. Does it make sense for everyone? Say, all of you, are you getting the idea? So in this way, if you keep on calculating 1, 2, 3, 4, 5, 6, so on. So add the number, say, let us take with 10. So 10 into 1 comma 1, so 10 comma 10, nothing but applying the modulos 1 comma 2. So not equal to the 0 element. So if you take 11 comma 11 under multiplication modulo 3 and modulo 4, it is 2 and it is 3, not equal to 0. If you take 12, it is 12 comma 12, applying the modulo operation, it is 0, 0. Here you will get the value 0, 0. So you keep on multiplying with 1, 2, 3, 4, so on. So at the number 12, you will get 0, 0. On the first element, I am applying multiplication modulo 3. And second element, I am applying multiplication modulo 4. So is it clear for everyone? So hence the characteristic of the ring is nothing but 12. Fine. Please take a note of that. After noting, please tell. Any questions from anybody? Say. Any doubts? Any questions? So here we can observe one thing, that if you observe the numbers 3 and 4, what could be the LCM of them? 12, isn't it? So whenever you take the values under modulo, you can say LCM would be the characteristic. That you can cross verify. And I will ask one more question, that so if you take the ring Z cross Z, what could be its characteristic? What could be its characteristic? So whenever you have taken the pattern, say Z4 cross Z6, what could be the LCM here? 12. So characteristic is 12. So while deciding the characteristic, you should know the characteristic of the sets individually. So what is the characteristic of Z? What is the characteristic of Z? The set of integers? 0, isn't it? Because Z is an integral domain. So here the characteristic is 0, here it is also 0. If you consider LCM for these two, the result is also 0. So the characteristic of the ring Z cross Z is nothing but 0. Okay? Now does it clear for everyone how we are calculating the characteristics? So at this point, I want to conclude our today's session, and tomorrow we will view the next topics and some results also. If you have any other queries, you can ask. Any doubts, any queries for you? So thanks to everyone.